energy resources. Mr. Dalton, are you able to show your camera? Great, perfect.
Yes, thank you for the introduction and thank you for the opportunity to be here to present today. The questions that people were just raising are a great segue into some of the topics I'll be discussing here in terms of inverter functionality, managing voltage on the system, and a range of other topics. So next slide, please. Just starting with a few of the key takeaways in mind. The first is that DER integration considerations really vary by technology type and use case. We'll look at a few of the main types of technologies and how that impacts the integration considerations. Secondly, there's really a standard set of physical and control impacts that grid modelers and planners look at. Sometimes the thresholds are a little bit different, but in terms of the fundamentals, it's pretty similar across the country. So we'll look at what some of those impacts are and how to mitigate them. And then also thinking about control systems, there are kind of autonomous, the inverters controlling reactive power, trying to manage voltage on its own, and then there's centralized systems. And really, it looks like the future is some sort of combination of these decentralized and centralized controls when we think about integrating DER. And then finally, interoperability, or the ability to seamlessly exchange information for monitoring and control is really a key to integration in the future. So next slide, please. Actually, we can just advance to looking at the types of technologies. I've sort of boiled this down into two main types. We have rotating machines on one hand, and these are sometimes called synchronous generators, induction generators, and they physically have a rotating mechanism within them that is using electromechanics essentially to produce power. So it has a mechanically coupled response that's related to the speed of that rotation. By the nature of these devices, these rotating machines, they have a lot higher fault current. So if we think about protection, impacts, and a large amount of energy when a tree drops on the line or a squirrel or whatever causes a fault, that fault current is quite a bit higher than inverters. And these also have a very well-characterized fault current response that's based on the physics of the device. And they can sustain islands. They're actually a voltage source. They can create fundamental voltage on the system that can energize loads, and inverters can follow this fundamental voltage. However, rotating machines have very limited reactive power capabilities, especially for trying to lower the voltage or absorb reactive power. So there are limitations based on the stability of the devices. Inverters, on the other hand, are software defined. They're very highly configurable. The fault currents are quite a bit lower. So if we want to compare rotating machines to inverter machines, rotating machines can often have like 6 to 8 times the fault current, so quite a bit higher. And then inverters, since they're software defined devices, the fault current response when there's a problem on the grid greatly varies by the particular manufacturer and how that device was designed. Grid interactive inverters aren't able to sustain an island or energize loads that are disconnected from the broader grid. They're really relying on that fundamental voltage from the grid in order to operate and supply current into the system. But they are, again, very flexible, so they have a wide range of these reactive power capabilities, which we'll talk about in the context of smart inverter or advanced inverter functions. So next slide, please. Zooming in a little bit further on the inverters, we won't go into the details of that block diagram in the upper right, but what I did want to convey with that is that these are largely software defined control systems again, and what they're doing kind of at the fundamental level is creating a voltage or a current waveform, excuse me, by kind of quick pulses, and that's what's in the lower right hand of the screen. And so they can really, create this current waveform and either match it up directly to where the voltage is, and then there wouldn't be any reactive power in that case, or advance or delay the current in terms of voltage. And that's really, when we talk about reactive power, which we're going to get into a little bit further, that's really all it's doing. So the software defined controls of these current devices allow for very flexible operation over a wide range of conditions that contribute to kind of the voltage control that was just being discussed as well. Next slide, please. Rotating machines are still being deployed out there a lot of times for backup power, so they're not paralleled or connected to the system as frequently as inverters are. But since they're still part of the system, figured we'd spend just a minute looking at how they operate. So as I mentioned, these are rotating devices that have basically magnets in them and windings. And if you take a winding and you pass it over a magnet, you induce an electrical current. That's really the fundamental mechanism for these devices generating power. But they have a lot of physical limitations that we were just discussing in terms of managing grid voltage because of the rotating nature and the electromechanical nature of these devices. They are used in terms of like DER sometimes in hydro units, and induction machines are sometimes used in wind units, but even those types of DER are starting to transition over to inverter-based interfaces more and more often. So on the next slide, please. I'm going to very briefly talk about energy storage, and there are going to be kind of full presentations on this topic later, so keeping this part brief. But what I did want to flag about energy storage is that it's introducing additional control systems on top of the inverter control system. So it's basically adding another layer that increases the flexibility of the devices, and also need to manage, thermal constraints and estimate what the capabilities of the device are. And also wanted to point out that there's a draft IEEE standard P1547.9 that is providing guidance, or will provide guidance when it's complete, on energy storage interconnections and the specifics of energy storage compared to all other DER. So that may be available sometime mid to late next year. Next slide, please. Then in terms of, and this is probably intuitive to a lot of the folks on the line here, but solar PV is really driving inverter-based generation growth in the United States, and specifically looking at DER, which is the data represented on this slide. Solar DER is the largest capacity sector of all the DER, and all solar is going to be inverter-based. The other technologies could use an inverter interface, or they could rely on sort of more traditional rotating machine technology. So the point here really is that inverters are a growing and important part of the system, and thinking about how to integrate them is going to continue to be an important aspect here. Next slide, please.
Hi, Mr. Dalton. Before you move on, we did have a question. When you say that inverters are not able to sustain islands, does that include intentional islands with hybrid DERs, solar and storage?
It's a great question. So when I say inverters can't sustain island, it's caveating that they're grid interactive inverters that are certified to a specific certification, UL 1741, that tests specifically that they are not able to sustain an island, that they can detect and disconnect from the system. There are other inverter designs that are intended for island operation, and that could even be within that same inverter device, that when it switches over to an intentional island operation, that it's actually changing the mode within the inverter. But if it was in that intentional island mode, it's not in the mode that would be certified for grid interactive operation. So yes, there are certain designs that can, but largely when utilities are looking at interconnecting inverters, they're assuring that they're not able to sustain an island.
Thanks.
Yep. Good question. Yeah, next slide, please. So very briefly, when I think about a progression of integrating DER, in my mind, I break this down into at least a few different steps. Initially, there's really the physical connection and making sure that for how that device is connected in a normal operating mode, that there aren't going to be thermal protection or voltage types of issues. Interconnections, however, typically don't look at contingency configurations. So if there were switching, like we'll look at later in an example, that's not really accounted for. So a next step is to really think about how to integrate DER more broadly into planning and operational frameworks. So that could be contingency operations. That can be making sure that we understand what amount of load is hidden from a DER contributing to providing energy on the grid, and sort of larger system issues like ride through. Even further in the progression is really how to use the DER as an integrated resource for things like non-wires alternatives, avoiding traditional utility investments or market services like frequency regulation or other kind of advanced services. Next slide, please. Looking at sort of the fundamental operation of inverters, kind of that the interconnection piece of integration, what we're looking at here is a common voltage profile before there's DER. This was shown in the last presentation as well. Next slide, please. When we add DER onto the feeder, there can be reverse power flow, and that can elevate the voltage in the area where the DER is producing power. Next, please. There are really kind of two ways to reduce voltage from the DER perspective, setting aside other types of mitigations. Next slide, please. The first is for the DER to consume active power. So now we sort of have this opposing effect where the DER is injecting active power and consuming reactive power. And there's a cancellation effect in terms of the voltage rise that can occur, and how effective that is really depends on the system characteristics in the area. Then next slide, please. The second way is less preferable, and that's to reduce the active power or the watts, the part of power that a DER owner is compensated for. So this is generally reserved as like a backup option, and we'll talk a little bit later about how these reactive and active power functions can be stacked so that there's a primary response related to reactive power, which doesn't affect the output of the device if it's designed properly. And then as a backup option, sort of curtailing the power in real time. Next slide, please. And then thinking about sort of the planning and operational needs that arise, situational awareness, at least on the operational side, is a big one. And what we're looking at on the screen here is an example of two substations that are connected together through normally open switches. Those are the open white boxes. And as we can see, there's DER on feeders from the blue substation and one from the red substation. But if there were a need to de-energize that blue substation for maintenance, or there's some sort of issue, a transformer fails. Next slide, please. The system could be reconfigured. So whereas that large PV unit that was close to the blue substation may not have had an effect on voltage just due to where it was located, now that reverse power is going on a different feeder, and it could be quite a distance from the substation based on how it's reconfigured. And I mentioned that studies don't always account for these contingencies because there can be so many for even just a set of two different substations that it can be, with current tools and methods, not always practical to study all the configurations. So that really leads to a need to be able to monitor the voltage and the power output, the current output at these different locations, to be able to have that awareness of if you've needed to reconfigure the system, if there's potentially a voltage or a thermal issue created by DER, which we want to try to keep online even in abnormal configurations to the extent possible. But the tools are still really evolving to be able to do this well. ADMS is one of the largest solutions out there. Next slide, please. And what ADMS can facilitate is the monitoring, the direct monitoring of meter devices, or the DER itself, but it can also perform estimation for DER that's not monitored. So thinking of all the rooftop units that might be numerous and not very practical to monitor every single one of those, at least today. Having some idea, an estimated quantity of how those are impacting the system is another important feature of a system like ADMS and can facilitate this type of situational awareness. Next slide, please.
And I think before we get into your next session, we will poll the audience. You had a really good poll for you to be a little bit more informed of what the audience is like. So I will, we're pulling up that poll right now. It reads, to what extent has your state started planning for and integrating advanced DER controls? The options are if you adopted smart inverters based on California or Hawaii state standards. Option B, modifying DER technical standards to prepare for equipment availability. Or C, we have active proceedings on the use of advanced DER control. And once we get a sufficient polling number, we will reveal the results. So I think, yep, the poll is closing and majority of folks said C. There are active proceedings underway. Thank you.
That's great. Thank you for that. All right, so moving into the standard control capabilities that will help facilitate DER integration, and by standard, I mean that these are based off of the IEEE 1547 2018 revision that is going to result in equipment availability, most expect sometime around the beginning of 2022. There are 5 different functions that all rely on kind of those 2 basic mechanisms that we discussed a few slides earlier of either controlling active power or adjusting reactive power. So we're going to zoom into a couple of these, the volt var function and the volt watt function, which are offering a lot of promise as standalone functions, but also as coupled functions. You can couple one from the blue category with the red category, but everything in the blue kind of voltage and reactive power control, those are mutually exclusive. So let's first dive into volt var on the next slide, please. What we're looking at on the screen is the characteristic curve of the volt var function. What we have on the vertical axis here is reactive power that's either being injected or consumed by the DER. And on the x-axis here, we have the voltage of the system. So for higher voltages, the DER is going to consume reactive power, pull it from the distribution system, and that has that sort of cancellation effect that we discussed by opposing the direction of the active power flow. Next slide, please. And looking at an example of how this would operate dynamically over time, we're going to show a brief animation here, but I'll orient us to what these different graphs are before we hit go on it. Starting in the upper left, this is showing simplified loading of a distribution circuit over time. And below that, we're seeing basically an inverse curve where the voltage is going to be higher at times of low loading, and the converse is also true. And then if we watch this volt bar curve on the right-hand side, that red dot is basically the operating point over time. And just to illustrate that this is a dynamic function that is going to react to the voltage. And next slide, please. So as we see, the voltage is high and we were absorbing current briefly, voltage goes low and we're injecting reactive current. That's basically the operation of the volt bar curve. It's going to sit there constantly monitoring the voltage and react with current over time. Next slide, please. We'll play it one more time so in case you didn't catch it. So it's responding with a 5-second open loop response time. So it's not extremely fast, but it will help manage voltage, at least locally. The next function is this volt watt. And again, we're looking at the characteristic curve where for normal voltages, we have active power on the y-axis. The DER is just going to be operating at its full rated power. But if voltage exceeds some threshold, V1 in this case, the power starts to be adjusted downward to try to help manage that voltage locally. And let's, on the next slide, please, going to look at an example of this. So on the right-hand side of the screen, we have kind of similar to a few slides earlier where there's two different substations. The green box in this case is a normal open. So we have DER being served from that red substation at the top. Voltage is great, everything's fine. Next slide, please. But then we have an issue with the red substation. It struck by lightning, let's say. Next slide, please. We have automation in this case, let's say. So the fault is isolated. Next slide, please. And our DER is re-energized now from that blue substation at the bottom. But now that it's so far away, the DER is so far away from the blue substation. Next slide, please. We have the potential for a high voltage. So let's just assume that the voltage goes up to 107% of the nominal voltage. What we would see with this volt watt activated is an automatic adjustment of the power output from the DER to drop to a lower level, to try to help contribute to mitigating voltage rise in this case. So this function could be very helpful for these abnormal configurations of the system that we haven't studied during interconnection analyses in order to provide some sort of backup soft shutdown function. Next slide, please. And then thinking about stacking these functions, the volt var function is best suited for sort of day in and day out operation of helping affect the voltage. It's unlikely to be able to really actively manage the voltage, but by controlling reactive power, it can contribute and affect that voltage locally and help reduce overvoltages and avoid potential mitigations that might otherwise be needed. On the other hand, volt watt is really reserved for abnormal system voltages to act as that sort of soft shutdown. Next slide, please. So what we've been discussing so far is all related to sort of local system, and we're going to very briefly, looking at the time here, cover some of the bulk system perspective. And the bulk system has sometimes opposing operating objectives to the distribution system. So it's an important discussion point between distribution system operators and transmission, how to really configure these bulk system responses. Next slide, please. But just to give a flavor of what the responses are, there are standard operating regions defined that contribute to bulk system reliability by having the DER sort of pull in the same direction as the bulk system needs. So we won't go into these regions in detail, but this was a change in IEEE 1547 as well. And next slide, please. These bulk system functions offer a lot of configurability in terms of what the set points are. And MISO actually went through an exercise stakeholder process to develop guidance for where these undervoltage trip settings, in this case, should be modified to be placed. And this has been common in other ISOs and RTOs, as you can see in the bottom right-hand corner, a little key of other set points to modify these undervoltage, but it is interesting that the defaults aren't really being accepted for undervoltage, and there's these stakeholder discussions to really figure out where these should be placed. Next slide, please. Now, transitioning into sort of interoperability, monitoring, control, management. Next slide, please. What's in scope of IEEE 1547 and is going to be defined is really this interface between the DER and the system. Everything upstream is out of scope. The network, what's going on in the backend system, that's all out of scope. Next slide, please. And in terms of what's in scope at that interface, it's really defining the monitoring, control, information exchange requirements, information models, so everyone's sort of calling an apple, so to speak. And then also the protocol, what language are we speaking in, French or German or English when we're referring to that apple. Next slide, please. And briefly, these are the standard monitoring and control and information exchange capabilities that all DER will have. So there's sort of the nameplate information, what am I, the configuration, changing all of the settings that we talked about for those advanced functions, monitoring, what's the real-time output, and then management is a different set of functions. Next slide, please. And how will this interoperability be used? It's really sort of monitoring that real-time operation, situational awareness. If you need to do remote settings changes, the initial settings don't work. The tie-in to ADMS and DERMS, which we'll very briefly look at. And then flexible interconnections as well, if we want to command a power level to DER based on the real-time conditions. That's another advanced use case. Next slide, please. Very briefly, just have a couple slides left looking at the time. In terms of accounting for DER and an ADMS, we talked about this briefly, that hidden load issue, but DER also poses other challenges for ADMS. For example, the FLISR module that the previous presenter was talking about, DER can interact with those modules, so it needs to be accounted for properly. Same is true for voltage regulation or integrated volt VAR optimization. There really needs to be close coordination. Next slide, please. And then in terms of like, where do ADMS and DERM systems fit in? Here's one view of how DERMS, ADMS could interact with aggregators or even directly with DER devices. And there's going to need to be a growing focus on cybersecurity as all of these devices are networked and connected. And then some of the advanced functions, just thinking back to that three-step process of integration, the advanced functions are likely to rely on these types of systems to perform market services, non-wires types of solutions. So there's an expectation these systems are going to be increasingly important as time moves on. And that's my last slide. So same key takeaways as earlier, and conscious of the time, I'll hand it over. Thank you.
Thanks, Mr. Dalton. And we have a second presenter for this section. There's more resources here for your information on the slides on LBNL. And Ms. Langner, please take it away.
Great, thanks, Carrie, and hi, everyone. I'm Rois Langner, and I'll be talking to you today about how buildings can be a grid resource. Next slide here. So I am, sorry, one before that, I think I had an intro slide.
Rois, we move those to the back. Consistent.
Oh, okay. No worries. I'll give a little background to myself first before I move forward then. I'm a senior engineer in the Commercial Buildings Research Group at NREL. I'm an architectural engineer and a building scientist, so I am coming at you from a different perspective here, and really thinking about this integration, management, and control of distributed energy resources. I want to talk today about how buildings themselves can be this resource to the grid, and how we're thinking about that from the National Lab level, from the Department of Energy level, on how buildings can be more flexible and how they use energy to really provide that resource to the grid. Next slide. A few objectives for today's call. So we'll be looking at what are the impacts of buildings on the grid today. How can buildings be flexible in how they use energy? And what are some more dynamic signals from the utilities that can be used to help better manage buildings' loads? Next slide. So in this next slide, thanks to Lawrence Livermore National Lab, I'm sure many of you are familiar with this, but I like to present this because this really shows our estimated energy consumption. This is from 2019, and on the left side of the slide, you can see the different fuel sources that enter our grid. Out of the total energy, I like to think about three different buckets of uses here, and those are located in the pink boxes on the right side of the slide. So buildings, both residential and commercial, consume about a third of our energy. Industrial processes, which does include buildings, consumes a third. And transportation, which often transports people and products to and from buildings, is about a third. So buildings consume a significant portion of our total energy use, and as far as our electrical generation, they actually consume about 75% of what we generate in the US. Next slide, please. This slide is just showing how buildings consume energy and how that's changed over the years. Since 1980, we've seen more than 35% increase in residential energy consumption and more than 72% in the commercial side as well. Of course, that's because we've had a lot more construction happening across the nation, but it's been a serious jump. And with that, we've had a lot of focus in the past on energy efficiency and how do we reduce building energy consumption. But now we have more and more variable renewable energy generation coming online. We've been having, as many of us have been following the news, extreme weather events and other natural disasters that are hitting more frequently. And there's just much more urgency for buildings to not just consume in our normal manner, but to coordinate our consumption with the grid needs. And they can. The next slide. And that's what I'm going to be talking about today. So a little shift in focus here, but how can buildings be interactive and efficient? And we've heard this term in the last presentation, the grid interactive efficient buildings. The acronym is GEBS. There's been a lot of opinions on that acronym, and I actually really like it because of this pairing of two keywords, and that's interactive and efficient. So I'm going to talk about what are GEBS, why are they important, and what are the benefits to both the grid and the building owner. Next slide. So when we talk about GEBS, GEBS are really about enabling buildings to provide flexibility in energy use and grid operations. 80% of grid peak demand is driven by buildings. A little more than 10% of grid infrastructure costs are spent to meet the peak demand that occurs less than 1% of the time, making those peak times the most expensive and likely carbon-intensive power. In addition, on the consumer side, on the building owner side, they can see demand charges that can be up to 60% of their energy costs. So it's now this growing importance that we must focus on building peak demands and how to manage that in a more in a better manner that works with our grid. Next slide. So some key characteristics of GEBS. As in the title, GEBS are efficient. So I'm not going to spend much time on that. That's just reduce our energy consumption. They are connected. And I'll pause here because this idea and concept of a smart grid has been around for years and years, actually. It's not a new concept, but I do believe that now we actually have the technology and the analytics to really push forward our buildings. We have equipment that are IoT enabled and connected. They offer two-way communication between equipment and a building automation system or a home energy management system. We have advanced analytics that really enable the smart operations that are often supported by multiple sensors and controls that are more readily available on the market these days, and we can optimize our efficiency and the flexibility while maintaining occupant comfort in buildings. So all of this together and paired with some of these distributed energy resources like PV and battery systems, we can really operate our buildings in this more flexible manner, reduce our energy consumption, shed the load, shift it when we need it on an hourly basis throughout a day. Next slide. In this next slide, I'll just show a couple examples of what types of systems can be controlled in more flexible manners. And it's most of the systems in buildings. This is representative of a commercial building in this case. And I'll talk through this in more detail in some of my later slides. But HVAC systems, there's a lot of opportunity to ramp fans down, for instance, or stage operation of equipment so that they're like electric resistance heaters so that they're not operating all at the same time, or setting different set points or pre-cooling, preheating a building to shift the load to off-peak times. We also have the capability to work with our lighting systems to turn lights off, reduce the lighting load, just dim the lights a little bit so it's not that noticeable to the occupants. We can rely on battery-powered equipment, plug-in battery-powered equipment like laptop computers or even electric vehicle charging. Can we use those batteries to our advantage so that we could shed load during different times of the day or shift the charging to another period of time when it's more appropriate. Thermal mass is a huge component or attribute of the building that we should be taking more advantage of, whether through water heating systems or through the actual inherent thermal mass properties of the building itself, concrete floors or other mass just in a typical building. Can we use that to store heating and cooling so our systems don't need to run as hard during peak time? And with this, we're getting smarter equipment in our buildings. The equipment is better connected to our automation systems, our home energy management systems. So we have this two-way communication between specific equipment inside the building, but there's also this capability with other communication protocols such as OpenADR, where we can communicate with the building to the grid and receive signals from the grid on when to reduce the energy consumption of the natural building. Next slide. So there's 4 demand flexibility modes that we really highlight here. First one is energy efficiency. Of course, this is just reducing the load profile of a building. Load shed is what we're more interested in as we talk about GEBs and load shift and modulation. So load shed is just reducing our peak load for short periods of time throughout the day, so a couple hours perhaps. This can change on a weekly basis or depending on the day of the week, and it might have seasonal impacts as well. Load shifting, similar, it might, the time of day that we can shift load, and a great example of this is pre-cooling a building. So running the chillers in a building during off hours, maybe at night, to pre-cool it. So during the heat of the day, a building is not running their chillers quite as high. So that's just shifting the load to these off-peak hours. And then modulation is this very slight increase or decrease of the building's power at the sub-seconds level. And this really provides this grid resource for balancing load on the grid. As various loads come onto the grid and come off to the grid, buildings can respond and provide this slight modulation in their own electrical load to help offset that. Next slide. So when we combine these together, and again, these slides are representing our load profile of buildings. So efficiency, we're just dropping that load profile. When we include the generation side, renewable generation like PV, we are often stuck with what we're calling the duck curve, right? With these drastic drops in energy consumption and drastic rises in energy consumption that the grid needs to accommodate. So when we can be smarter with how buildings use energy and more flexible in that, we're really trying to even out that curve. So we're not seeing such drastic spikes and dips in the energy consumption in aggregate, and we can even that out to more predictable loads that the grid can accommodate, and especially as we have more and more variable renewable energy that's coming online. Next slide.
Sure, and I think you have polls after this slide.
After this slide, okay, great. So potential benefits, there's a number here. I'm just going to focus on a few of these, but really on the grid side, if we can be more flexible with our energy, it does provide us improved reliability and resiliency of our electrical infrastructure. It reduces grid congestion. There's even environmental benefits if we can use energy during cleaner parts of the day, so we can actually reduce the greenhouse gas emissions or use energy when those greenhouse gas emissions are lower. On the building owner side, I think it really comes down to this energy affordability side of things, where we can really focus on peak demand and continuous peak demand management and reduce those peak demand charges. So with that, I think we can go into the poll questions. I just have a couple here to gauge your engagement on this already. So does your state currently consider buildings as a grid resource? 3 responses, yes, you're exploring leveraging flexible buildings for peak load. Not sure, you're new to this topic, but excited to explore these opportunities. And no, flexible loads do not enhance business or operational needs. Great. So this is excellent. So it's great to see that even 6% of you are exploring leveraging buildings for peak loads. That's great to hear. I'm not surprised that 71% is not sure. This is a new topic, and that's helpful for me for how much detail to dive into here. And also interesting to see the 23% no response here. And I would be curious maybe in the discussion later to explore that a little bit more to see if you think that your business or operational needs will change down the road. And then do we have the other poll, or are we continuing on here? Okay, great. So the second poll question here is, what do you think the largest barrier is to implementing demand flexibility? I've included a number of responses here: engaging building owners, technology limitations, utility rate structures to incentivize peak load reductions, and integration of renewable generation and battery thermal storage. Great. Utility rate structures to incentivize peak load reductions has 57%. Building owner engagement is 26%. Integration of renewable generation, battery, thermal storage. Yes, I see that. And nobody chose technology limitations. And I think that goes back to my point as we're ready to move forward with this on the technology side. But there's a lot of other hurdles that we do need to address to actually make this happen. So thank you for those responses. Great, thank you. And then next slide. So I do want to point out, as I just mentioned, we are advanced on the technology, but I want to talk through some of these inherent building pieces of equipment and end uses that can be controlled in these more flexible manners. On the residential side, we all live in the home, so I think we have some personal connection here. But thinking through smart thermostats and how those can be leveraged to modify temperature set points and preheat, pre-cool during off-peak hours. There's smart appliances to shift operation. Electric lighting, of course, can be turned off or dimmed. Water heating and thermal storage can be leveraged to shift heating and cooling loads associated with heating and cooling the house, and then also water heating. And of course, electric vehicles and chargers, there's a lot of research happening now too in thinking through optimizing charging of electric vehicles and when the best times are and how do we coordinate that with the grid depending on the building type and the operation. Of course, battery and solar PV contribute to the load flexibility as well. And next slide. On the commercial side, it's similar in that we can control our lighting to dim light shed capacity there using automatic window shade devices. On the HVAC side, there's a number of strategies that we use, of course, with temperature set points, leveraging thermal energy storage, and then staging of certain equipment like air handling unit fans or electric resistance heating so that they're not all running at the same time. And if you think of a building that does have electric resistant heaters, for example, you can maybe run 20 or a third of the electric resistance heaters for 20 minutes during an hour, and then shift to the next third, and then shift to the next third. And that drastically reduces that energy load of the building. Again, can we leverage equipment that has batteries to shift loads, shift the charging of those equipment to better times of the day? And how do we better integrate our solar PV and battery storage to really optimize performance for both the building and for the utility as well? Next slide. So in summary here, we really can leverage existing equipment in the building. Some of these technologies may or may not be smart. You can do manual controls, or you might have technologies that could communicate with an intelligent control platform or a building automation system. These technologies may offer one or two-way communication with the grid, and I think we're going to see more and more technologies like that on the market. Moving on, building managers can control these individual equipment, or they can leverage software solutions, which I'll talk about more in a moment, that can really optimize multiple end-use systems. And flexibility can be provided through response to specific demand response events that the utility is sharing with the building owner, or they can continually manage their demand on their own, which does provide more financial incentive to the building owner. as far as reducing demand charges and overall energy use of their building. We've really operated and modeled buildings in a very static way until now, and now we really need to think about how do we think through more dynamic signals that can be leveraged to optimize the building energy consumption. So these dynamic signals, of course, include time of use utility rates if they're available, or near real-time carbon emission rates, or weather signals and occupancy signals within the building. So again, we're moving towards this. We have the capability to have the analytics to think through those dynamic signals more critically and control in a more optimized manner. Next slide. I want to share a little bit about how the national labs are thinking about how do we characterize these gas technologies and solutions. And this gets in the building science weeds, but I think it's important to see how we're thinking about this and how it could relate on the larger grid scale too. But the way we think about it, these technologies is what is the capacity of flexibility that these technologies offer with the functionality, what end uses are targeted here, what types of flexibility modes are supported. Important ones are the communication protocols that it uses to communicate within different devices in a building, and then also to a utility. More relevant, I think, to the utility side might be the response time that a building could have to a demand response event, and how that building can ramp down or ramp back up quickly to respond to those signals. And we're starting to really test this, and I'll talk about some field studies that we have underway right now moving forward. Patrick also mentioned cybersecurity. This is always a huge question in mind when we start implementing these connected smart technologies in our buildings. Next slide. So talking about software solutions, we are seeing more and more comprehensive software solutions that are coming onto the market. Carrie, I'm not sure if you heard me, but if you could advance the slide, that'd be great. These software solutions connect to building automation systems or home energy management systems. They are touting that they can control multiple building end use systems. They may offer one or two-way communication with the grid. They're providing these advanced analytics for the flexible control. They trend the data. They capture multiple signals, occupancy, weather, utility rates, trended load data, carbon emissions. They have the capability to do all of this. So I'm excited to see that, because that seems like a more comprehensive solution and easier solution for the facility manager, and a more enabling solution that can really connect these individual buildings to a community of buildings, and that community of buildings to the grid, so that in aggregate, these flexibility modes will have more impact to the grid. Next slide. So the end goal of all of this is that we are looking for more flexible and optimized performance. How can we be more responsive to the building and grid needs? And really, how are we reducing our peak demand and lowering demand charges? Next slide. And lastly, before I wrap up, I have a few slides on this, but I wanted to briefly talk about some field demonstration programs. Looks like my slide is, I don't know if that's coming through on your end, but there you go. The General Services Administration, Department of Energy jointly release a request for information every year. We actually just released a new RFI focused on resilient and efficient technologies. So if you haven't seen that, that is out there right now. If you go to GSA's Proving Ground website, you should see a link to that RFI. But last year's was focused on GEB solutions and more of these comprehensive software solutions that enable multiple flexibility modes and integrate multiple building systems that go beyond integration of just HVAC and lighting, and that can dynamically manage and coordinate the loads. Next slide. So from this RFI that was released, we selected 5 GEB solutions, the software solutions that we will be demonstrating in real buildings. 4 of the national laboratories will lead the measurement and verification, including NREL, Lawrence Berkeley, National Lab, Pacific Northwest National Lab, and Oak Ridge. And we will be testing these in both federal GSA and non-federal buildings. Next slide. And because these are so complex, they're just highly complex solutions, we're really trying to understand what the capability is of these solutions to enable efficiency and load flexibility continuously and in response to DR events. What are the costs of these solutions? Does it meet the building owner needs? Does it provide utility benefits? And is it pretty easy to integrate? So we will be working with utilities on these projects as well as much as possible, and with those utilities that are interested in participating in the project. And I'm just really excited for these field demonstrations. They're really the first field demonstrations in looking at load flexibility and how these software solutions can actually perform in real buildings. So stay tuned for that. And my very last point here is, what we've recognized in this new field of load flexibility is it's really important to coordinate our language and metrics and our approach to measuring and verifying load flexibility. And these are going to be, again, complex. They're different building types. They have different uses. They'll have different equipment. They'll be looking at different load flexibility modes. But we've come together, and we, as in the National Labs, GSA and DOE in particular, Lawrence Berkeley has developed a lot of metrics around how do we quantify demand flexibility, load flexibility. NREL, Lawrence Livermore, Pacific Northwest National Labs help too. And these are just some of these metrics that we'll be looking at a higher level so that we can better compare these solutions in field demonstrations and share what the potential is in those unique scenarios in meaningful ways. Great, and last slide here. I just want to point you to a few resources for more information. So DOE has what we call their GEB site. This is a repository of all of their published report series focused on GEB-related work that the national labs and other experts in the field have put together. So this is a great resource to see what Department of Energy has done in this GEB space. The second bullet there is the Better Buildings Alliance Renewables Integration Team. So I'm the technical lead for this, and historically, this is really focused on strategic integration of renewables into buildings, but we've really shifted to this load flexibility, demand flexibility focus for our team. So if you're interested in joining our team calls, please contact me about that or go to our website to learn more. And this last one is a recent publication from Lawrence Berkeley National Lab on performance assessments of GEBs. So those are the 3, and with that, I'd like to thank you all for listening today, and I look forward to your questions.